In this video, I'll be talking about functions as vectors, and that we can treat these functions as vectors, and what functions are. Function, if we go to boil down things to the very basic level, it's basically the mapping of a set of values from one system to another system. So the mapping that we have, say 1, 2, and 3. So here, the argument is basically to inculcate a situation where we can realize that functions can as well be treated as vectors. And if we start with an argument and we take on the real numbers, say for example, we start with some real numbers as x1, x2, x3, so on and so forth. Now, this chain of numbers to infinity, and the difference between the adjacent numbers is infinitesimally small. I mean, the difference between the two numbers is extremely small, and uh, we will certainly regard these infinities in details in some other lecture. But here the motivation is that we have these these large number of real numbers as x1, x2, and so on and so forth, and they are very, very closely related to each other, and the differences between the 2 points is extremely small. Now, if we presume that we know some list of some possible functions, we can write out the functions as the corresponding list of values. So if I choose, say for example, I choose a column vector. If I choose a column vector, say f of x1, f of x2, and so on and so forth. So we have a column vector of functions from x1, fx2, and so on and so forth. Now, what is important here is that we could specify these functions. We could specify the function points spaced by so small amount. So I can think of that smallness using delta x. So the argument is I have a chain of x1, x2, and so on and so forth. The argument is that this x21 is x1 plus this delta x. And x3 is x2 plus this delta x, and so on and so forth. And for sufficiently many values of x and over a sufficient range of x, what we do is we want to get sufficiently useful representation of some kind of calculation for this chain of values that we have. And the right argument here will be integral. The right argument will be here integral, and the integrand, if I take the mod of f of x whole square, and its integral can be written as integral of mod of f of x square dx. And how we can write it in terms of matrices. So what we can have a column matrix, f of x1, f of x2, and f of x3, and so on and so forth. And we'll multiply this with a row matrix of these functions, f star of x1, f star of x2, and so on and so forth. Now, star means the complex conjugate of these functions. So, but what is important, we can see that this is an equivalence of this square integrable function. It's equivalent to the product of these two matrices, a column matrix and a row matrix. And what is important here is this equation could be treated as true only if we choose this delta x to be sufficiently small, to be extremely small. And the corresponding vectors therefore should be sufficiently long. And we can get an arbitrarily good approximation to this integral by choosing the matrix multiplication. Now, if we want to visualize these functions on a graph, and then we would like to translate these functions into some kind of vectors, the coordinates of a vector. So for that, if I take a simple example, say for example, I have a function f of x along y, and I have x along this x-axis, and let's assume that I have a plot like this, and this is my f of x, and then I have some values. Say if I treat this point as, say, f of x1 at x1, I'll choose another at x2, that's f of x2, and I'll choose another x3 at f of x3. And we can translate down this set of function, the three values that I have chosen here for the sake of simplicity, and I have some resultant vector f. Say I have some resultant vector, say it's g. No, let it be f. And this resultant vector has components x1, and say this is x2, and this is x3. So along x1, what I have is f of x1. Along x2 is f of x2. And along x3 is f of x3. So here we are thinking of a function in terms of its components. And in quantum mechanics, the functions are not real, they are basically complex. The functions are complex and they are not real. And there may be many elements in the vector. There may be elements more than that of the components that we have chosen over here. Possibly, it can be infinite number of elements in a vector. So, to proceed from here, what we visualize here is that we are trying to still visualize the function as a vector, and more generally the quantum mechanical states as a vector in some kind of space. So if we move on from here, I mean, what we realize here is that a function, a set of functions, can be treated as a vector. That's the motivation here. So here, if I choose this as the resultant of the three vectors, three functions, f of x1, f of x2, and f of x3. So in general, you can have set of large number of such elements that can resonate into a single vector. So that single vector in quantum mechanics is a result of those infinitely large number of elements present in that space.